All right, so really work on these things, okay? It's almost like I should have a coset property gateway, right? You want to work on this stuff really hard. You're going to get this weird stuff in chapters 7, 8, 9, and 10 especially, and later on, later chapters, where we do similar kinds of things. You want to get these properties internalized. You want to try to prove them all, and believe you could prove them all on the test. Here's another property. Do like the book says as well, try to practice saying these things in words. The left coset of H and G containing A equals the right coset of H and G containing A, if and only if these two sets are equal. If and only if H, the subgroup, equals this set, where that set, again, remember, is defined by the equation that looks like this. Set of all products of that form as little h ranges over big H. Is this important? It's actually super important. Okay? All these facts are super important. Chapter 9, we're going to see especially, this is fundamental to understanding group theory. Right now it just feels like something really weird. Okay? But it turns out to be fundamental. Finally, AH, the left coset of H in G containing A, is a subgroup of G if and only if A is an element of H. Same with the right coset of H and G containing A. That's what I mean by the analogous. I'm talking about with right cosets. This should jive with this. These two things should jive together, right? If H is a subgroup of G. When A is an element of H, not only is AH a subgroup of G, AH also equals H. It's the starting subgroup. H. The subgroup that you start. All right, I don't want to write out the proof of Lagrange's theorem in words. But let's just think about the key ideas visually. It's based on these properties of cosets. So again, Lagrange's theorem says if you've got a finite group of a certain order and a subgroup of that, the order of the subgroup has to divide the order of the whole group. If G is a finite group with, say, the order of G equaling n, and if H is a subgroup of G with the order of H equaling, call it K, the conclusion is that K must divide n. That's Lagrange. The idea of the proof, the proof itself, is based on properties of cosets. As you should have read about, and as you can see in that video, that extra video I pointed you to. Imagine this is G. The cosets partition G into a finite number of pieces of the same size. Same size based on this property. One thing I forgot to emphasize with this partition is, because it is a partition, there must be an equivalence relation in the background. Remember back in chapter 0? Equivalence relations induce partitions and vice versa. I'll say what the equivalence relation is in a minute. I'm now drawing these sets that in such a way that they necessarily have the same area. That's impossible to do. But they do have the same number of elements, so ideally I try to draw them so it looks like they have approximately the same area. But don't take that analogy too far, right? This is a finite set here, and so the area analogy isn't perfect. These are disjoint. Intersections between any two of these cosets is empty. And the union of all of them is the entire group. And they all have the same size. same number of finite elements. The key equations you need are that G is a union of these things, and these things are disjoint. The intersection of any two of them is empty. Therefore, you can say the order of G is the sum of the number of elements in these different cosets. But they all have the same size. And that size is the same as the order of H itself. And there's R of them. So you can say the sum is R times the order of H, since each one of these terms in the sum has the same value as the order of H. AI times H, the number of elements in that, is the same as the order of H for each one of these, for A1, A2, through AR. There are the terms in the sum. Again, these things all have the same value as that thing. Therefore, the sum can be written as this product. And that does it. That says that the order of H divides the order of G. Okay, I've got the, you can't quite see this visual. That's from one of the previous lecture videos. I drew that picture on the board before. With general partitions, based on general equivalence relations, these sets don't have to have the same size. They don't have to have the same number of elements. This is a special partition, a special equivalence relation. What is the equivalence relation in this context? It's that A is equivalent to B if and only if AH equals BH, which is true if and only if A inverse B is an H. By the way, again, the roles of A and B are symmetric. You can switch these around. That's true if and only if B inverse A is an H as well. That's how you would define the equivalence relation. And you should take the time to verify that it is an equivalence relation. That could be something that could show up on exam 2. You should be able to verify that this defines an equivalence relation. G. Okay, so the proof's not too hard, actually, once you get the idea of a coset down and the properties of cosets. The properties of cosets are really probably the hardest part, just to prove all those. Even though each individual proof is not too hard, cumulatively it seems like a tough thing. And it's kind of, since it's so strange, it's kind of tough to remember, too. Here's something I have not put up before, though I think I mentioned it verbally. Given a group G and a subgroup H of G, the number of distinct left and right cosets of H and G is called the index of H and G and is denoted by this notation. Again, weird, but that's what we go with. That's the notation for the number of left cosets and right cosets of H and G. The number of left cosets and right cosets will be the same. Note this can actually be a finite number even if G is an infinite group. As an example, the group of integers under addition is infinite. But if you consider the cyclic subgroup generated by, say, 3, for example, that is a subgroup of Z that has finite index. What are the distinct cosets? The distinct cosets are 0 plus the subgroup, which is the same as the subgroup, 1 plus the subgroup, and 2 plus the subgroup. 3 distinct cosets. 3 plus the subgroup would get you back to the original. 4 plus the subgroup would get you back to this one. 5 plus the subgroup would get you back to this one. I'm using additive notation here for these cosets because the group operation is addition. The index of this subgroup in Z is 3. There are 3 distinct left cosets. The proof of Lagrange's theorem shows that this equation is true. The index of H and G is the ratio. The order of G divided by the order of H. In the case where G is finite. You don't want to write, in the case where G is infinite, you don't want to write infinity divided by infinity. Don't do that. Okay? In this picture here, if this picture illustrated what was really going on, then the index of H and G would be the number of left cosets, 1, 2, 3, 4, 5, 6, 7. This would be 7 in this picture. And it would be the order of G divided by the order of H. So as an example of something that's consistent with that, if the order of G were, say, 350, and the order of H were 50, then that would be a situation consistent with this picture. The converse of Lagrange's theorem is false. Just because a positive integer k divides the order n of a finite group does not mean that the group has a subgroup of order k. That's true for cyclic groups, right? And back. True for cyclic groups, right? Fundamental theorem of cyclic groups says if k divides n, where n is the order of the cyclic group, then there will be a subgroup of order k. Not true in general. Is there a simple example where it's not true? Well, relatively simple in the big scheme of things. A4, which has order 12, it turns out has no subgroups of order 6, even though 6 divides 12. What was A4 again? A4 was the alternating group on 4 symbols, subgroup of the symmetric group on 4 symbols, group of permutations of this set. S4 is all permutations of that. A4 is the subgroup of all even permutations in that group, also called the alternating group. It's got 4 factorial elements divided by 2. 4 factorial divided by 2 elements, 12 elements. It's got no subgroup of order 6. The book proves that. I was hoping to prove it in class today, because it's kind of a cool proof. But I think for sake of time, I better not. It's a really cool proof. Probably one of the more interesting proofs we've had so far. It's on page 144. It's tricky enough that it would be tough to do on an exam without some hints from me. But I suppose if I gave you some hints, it could show up on the exam. So proof by contradiction. You end up proving that any subgroup of order 6, if such a subgroup of A4 existed, would have to contain all elements of order 3, of which there are 8 of them. And that's a contradiction. That's the big idea of the proof. If there were a subgroup of order 6, which would mean the number of left cosets would be 2, 12 divided by 6, you can get a contradiction. You can end up showing that every element of order 3 has to be in this group, but there are 8 elements of order 3. And they all have to be in the subgroup of order 6? Not possible. Contradiction. Make sure you study that proof. It's tricky enough that it would be tough to do on the exam without hints, but if I gave you hints, it should be something you should be able to do. Let's move on. It's something different though. Something called the Orbit-Stabilizer Theorem. I haven't covered, even in doing this, I haven't covered everything in chapter 7. In particular, this slide is something you should think about as well that you'll find in the book. Related to this set HK, where H and K are subgroups. But with the time we have remaining, let's look at the Orbit-Stabilizer Theorem. What is it about? Well, let G be a group of permutations on a set S. You've heard of stabilizers already, right? It showed up on exam 1. It was a problem, a completion problem to work on related to stabilizers. Comes up here. For each element of the set S, S is an arbitrary set, not necessarily a group. Could be finite, could be infinite. But you've got a group of permutations on that set. What are permutations? One-to-one and onto functions from the set to itself. Not necessarily operation preserving, right? Permutations are not isomorphisms, they're not automorphisms. They do map the set to itself, but with just one-to-one and onto. S is not necessarily a group either. The stabilizer is the set of all permutations that map I to itself. And you proved on exam 1 that that was a subgroup of G. Elements of the stabilizer are permutations. They are elements of G. Here's something new. Something called the orbit of I under G. Given a set S and a group of permutations G on S, define, this is supposed to be defined, not defined. Define the orbit of I under G by the set of all outputs of I under elements of G. This is a subset of S. It's not the image of some set under one function. It's the image of some individual element of S under many functions. The phi here ranges over all of G. If I is right there, phi of I might be right there. Maybe I should call it phi 1 of I. Phi 2 of I might be right there. Phi 3 of I might be right there. I'm writing phi 1, phi 2, phi 3 because I'm letting phi range over G. There's some set of group of permutations here in the background. All the elements that are possible images of I under elements of G are in the orbit of I. Why is it called an orbit? Maybe I'll talk about that next time. The Orbit-Stabilizer Theorem says that if G is a finite group of permutations on S, then for any I from S, we have this equality. The order of G is the product of the orbit, the number of elements in the orbit of I, with the order of the stabilizer. Notationally speaking here, this is the order of a group, and this is the order of a subgroup of the original group. This is not a group, or the orbit's not a group in general. The orbit's just a set. So when I use the absolute value signs around this, I'm just talking about the number of elements in the set. Consistent with the idea of the order of a group as being the number of elements in the group. This equation is true. There are pretty cool applications of this, mathematical applications that you'll see as you continue studying Chapter 7. Theorem 7.5, for example, gives you the group of rotations of a cube. Even maybe cooler, example 10 gets into the group of rotations of a soccer ball and figuring out how many elements there are in such a group. The sets in those cases can be taken to be the cube itself or the entire soccer ball, which can be thought of as being infinite sets. You can also, with the cube example, you'll see you can also think of the set that is being permuted around with permutation as being the set of faces of the cube. Rotations will permute faces around what you've got to label in, just like we did with rotations and reflections of regular pentagons and hexagons, etc. In our last few minutes, I want to try to give you the idea why this is true. this equation that you see here is equivalent to the following equation. Divide both sides by the order of the stabilizer, which is non-zero, by the way. Stabilizer always contains at least the identity permutation for any I. So we're not dividing by 0 here. But what's this ratio? By the proof of Lagrange's theorem, that's the same as the index of the stabilizer. In other words, it's the same as the number of left cosets of the stabilizer in G. So to prove this Orbit-Stabilizer theorem, we would be done if we could show that the number of elements in the orbit is the same as the index, the number of left cosets. We would be done if we could show these two things are the same. How do you show the two sets have the same size? And these are finite sets, by the way. At least G is, and the stabilizer is, and ultimately we would show the orbit is as well by showing this. How do you show two sets like this have the same size? You show that there's a one-to-one and onto mapping from one to the other. What is the one-to-one and onto mapping? We need to take an arbitrary left coset of the stabilizer in G. How would you write such a coset? Well, maybe something like this. Alpha stab G of I. That would be a left coset of the stabilizer, which is a subgroup of G. Alpha is an arbitrary element of G. This is the left coset notation. Take that arbitrary element and map to something in the orbit of I under G. What should you pick in that orbit based on this input to this mapping? Pick the only thing you can pick. Alpha of I. That's going to be in the orbit of I under G, right? Because it's an output. It's an image of I under some element of G. If you could show this mapping as one-to-one and onto, you'd be done. You don't have to show its operation preserving. It's not an isomorphism. If you could show it's one-to-one and onto, you'd be done. However, there's one thing to show first before you show it's one-to-one and onto. And this is the thing I'm trying to emphasize here at the end. You also need to show it's well-defined. Besides showing this mapping is one-to-one and onto, which would imply that these two sets have the same size. You would imply that the number of elements in the orbit is the same as the number of distinct left cosets, the index of G in the stabilizer, in G. Besides showing it's one-to-one and onto, we must show it's well-defined. What does that mean? That's a new idea. It means if I picked another coset representative here for the same coset, that I get the same image over here. It would get mapped to the same thing. This means if alpha times the stabilizer of I in G equals beta times the stabilizer of I in G, if I have two different coset representatives, they better map to the same thing. then alpha of I equals beta of I. In order for this mapping to make sense, that better be true, because you can have different representatives for the same coset. This can be true even when alpha and beta are different. In fact, by one of the properties of cosets, say it here, this is true if and only if alpha inverse beta is in the stable. For some reason, I keep writing my b's as n's. So that would be the thing you need to verify, that is, if this is true, then that's true. Okay, so lots of abstract ideas today. This is where it really gets tough, I think. This is one of the toughest parts of the course. Work really hard. We'll see you on Wednesday.